Okay, in the last class, we saw how to convert from one number system to the other number system. Always keep in mind that we are not focusing towards either the decimal number system or binary number system. We are always speaking in general, which means any number system is possible. A number system with base 5 is possible, 8 is possible, 9 is possible, even 25 is possible. So always we are speaking in general terms. So now let us do a very simple exercise that will make you slightly think. What is the decimal equivalent? Having seen the decimal to various number systems, can any one of you tell how to do this first problem? What is the decimal equivalent of 1221 to the base 3? So this belongs to base 3 number system. If you get some problem something like this, say for example 1 3 2 1, and if it is written as base 3, then basically this problem itself is wrong. Why? Because since the number system is 3, the number of symbols that are possible are 0, 1 and 2. Only these three symbols are possible. Since you are having 3 here, which means that this problem itself is a wrong one. Okay, now coming back to the problem. Can any one of you tell how to do this particular problem? 1221 to the base 3. You have to convert this into decimal equivalent.
So we will do 3 times the
Okay, 3
symbol
times.
raised to its weight, and we'll
Okay,
add all of that.
right. Okay. So this position corresponds to 3 power 0. This corresponds to 3 power 1. And this corresponds to 3 power 2. And this corresponds to 3 power 3. So, okay. So it is 1 multiplied by 3 power 3 is 81, right? So 3 3s are 9, 9 3s are, oh, 9 3s are 27. So 1 into 27 plus 2 into 9 plus 2 into 3 plus 1 into 1. So it is 27 into 1 plus 18 plus 6 plus 1. So it is 24, 25, 25 plus 27 is 52. Right? So 52 is the equivalent decimal value. So let us see the solution. Yes, it is 1 into 3 cube plus 2 into 3 squared, likewise, and then it is 52 to the base 10. Now, second question. How do you do this particular problem? The second one, that is 6e 6e to the base 16 plus c5 to the base 16. Yes, how do you do this? Normally, how do you do these kind of problems is you can add directly. 6e plus c5. Uh, so you have to keep in mind. So e corresponds to what? 14, and 14 plus 5 is 19. And what is the equivalent of 19 in terms of hexadecimal? You have to do it. Instead, what you can do is convert this into decimal equivalent, convert this also into decimal equivalent, add the both, and then convert back to hexadecimal equivalent. So the solution will be the decimal equivalent of 6e to the base 16 will be 110. How did I get this? How did I get this? Is multiply it with the weights. Okay. So that is 6e can be written as 6 into 10 power, sorry, 16 plus e corresponds to 14 multiplied by 16 power 0, which is 1. So it is going to be 6 6 are 36, 696 plus 14. So this is going to be 110 to the base 10. So that is how you got this one. So convert this into decimal equivalent. Similarly, C5 also convert this into decimal equivalent. You will have to do the same thing. So what is C equivalent to? C is equivalent to 12. So 12 into 16 plus 5 into 1, it is 16 power 0. So 12 into 16, how much? 192, I believe, right? So it is 192 plus 5, it is going to be 197. So you got this, you add these two things. When you add these two things, what is the sum of these two things? It is 70307 to the base 10. So they are adding these two things, you get 307. Okay, so now convert this back to the hexadecimal equivalent. So the hexadecimal equivalent will be 133. Okay, so this is how you do it. Similarly, the third problem. So how do you convert the decimal equivalent to hexadecimal equivalent? So 259.675 is a decimal equivalent. The hexadecimal equivalent, you have to do similar to what you did in binary equivalent. So 2598, you will successively you will keep on dividing this by 16 and then you will try to find the remainder. So that will be the integer part here. Now the fractional part, what you do is this 0.675, you will keep on multiplying it with 16 and whatever is the coefficient, the fraction decimal part, you will consider that as a coefficient. So let us see what is the solution here. So 2598 subsequently dividing it by 16. So it is 162, the remainder is 6. And 162 further divided by 16, it is going to be 10 and then remainder is 2. So A is represented as, sorry, 10 is represented as A and 2, 6 is the hexadecimal equivalent of this 2598. And now the fractional part 0.675, you multiply it with 16. So it is 10.8. So 10 corresponds to the coefficient part. So it is A26 is the decimal part and 10 here, use it as the coefficient here, and the remaining part is 0.8. You multiply it with 16, what you get is 12 and 12 corresponds to C, and then you repeat this particular process C and then it will C like this keeps on repeating. This is how you convert a decimal equivalent to a hexadecimal equivalent in both decimal and fractional part, sorry, integer and the fractional part. Okay, so we'll come back to these additional exercises later because this requires some understanding of signed numbers. Today we will start with a new chapter and a new portion in number system, which is called as a signed numbers. Before that, one more tricky question here. Okay, so you need to find out what is the value of x and y in this particular relation. So I am having a number system with base 9 and a number system with base 7. If these two numbers are equal, then what is the value of x and y? So how do you do it? How do you do that is, first multiply, you put some random numbers for this x, right? So let us, you can keep it as 20 to the base 9. Okay, so you convert this into decimal equivalent and then from decimal equivalent you convert back to the number system with base 7. So what is this decimal equivalent? So it is going to be 2 multiplied by 9 power 1 plus 0 multiplied by 1 is 0. So this is going to be 18. But we need something above 30, right? So 20 will not work. I'm just checking randomly. 25 to the base 9 is again 18 plus 5. Am I right? Because the first digit is going to be 9, 2 into 9 only. So it is 18. 18 plus 5 is how much? 22. This will also not work. So what will be the value that will be working? Let us check 28 now. So 28 will be again 28 to the base 9 when converted to hexadecimal, it will be 8 plus 8, which is going to be 26, right? So that will also, oh, okay. All right. So these are decimal equivalents. We have to check for, we have to convert them back to the number system with base 7, right? So this is decimal equivalent. Still we do not know whether they are equivalent to the number system with base 7 or not. Now you have to convert this into number system with base 7. So how do you do that? So keep on dividing it by 7. So 7 is how much? 2, 14. So remainder is 4. 2. Okay, so it is 2 and 4. 2 and 4 to the base 7. So 2, 4 to the base 7. So this number will not work. Let us check for 25. So 25, it is the decimal equivalent is 10 here. So 22 divided by 7. So 7 3s are 21. All right. So 7 3s are 21 and the remainder is going to be 1. So 31 we are getting. So 30 is also equivalent. Let us check for 25. So likewise you have to check randomly. If you check for 24, right? So the decimal equivalent is 22 to the base 10. You convert that into the numbers to the decimal, sorry, the number system with base 7. And how do you do that? You keep on dividing it by 7. So 3 and 1. So 31 to the base 7 is what is 24 equivalent to 9 is. And 25 also you check, you get 32 to the base 7. 29 if you put, you get 36 to the base 7. Obviously, for number system with base 7, the symbols that are possible are 0, 1, 2, 3, 4, 5 and 6. These are the symbols possible. Though 36 is possible, but here applying 29 is it is meaningless. Why 29 to the base 9 is meaningless? Because your number system with base 9 will have symbol only from 0 to 8 only. But here you are including 29. So which means this number itself is not a valid number in this number system with base 9. Okay, so that you have to take care. So based on this, these are the possible combinations of answer. Either x, if x is 4, then y is 1. If x is 5, then y is 2. Likewise, you can have different combinations of x and y for this answer. Okay, any doubt here? Okay. So one more example here. 2x to the base 5, you have to find 3y to the base 6. So again, you follow the same process. You substitute random numbers. When I say 5, then the number systems that are possible are only 0 to 4. Okay, so I'm applying 9 here. Again, this is an invalid number. It is an invalid number. I should not apply 9 at all. I should not even consider 9. Why? Because its symbols are ranging from 0 to 4 only. So, okay. And yeah. Okay. There may be a case. We have always been telling that these are symbols only, right? So at times people might use, we are considering only these symbols 0, 1, 2, 3 subsequently, right? You might immediately ask me a question, why don't I choose a symbol corresponding to say 8, 9, 7 and 6, so 7, 6 and 5. So you might ask me a question, can I consider these symbols and operate for a number system with basis 5? The answer is definitely yes, you can use it. But before you start this number system with these symbols, you must first define the weight of this number system. So weight of this basis. So you can consider this 5 to be the first base, 6 to be the second base, 7 as third, fourth and fifth bases, right? So as we do here, the weight of these particular numbers, then you can definitely proceed with that particular number system. Since that particular number system is slightly confusing, for the sake of convenience, we are considering a sequential number system from 0, 1, 2, 3 and 4. But there is no hard and fast rule that you should consider only this particular way of number system. So that is the reason in this particular example, you see here it is 2x power 5, right? So x here is considered as 9, though this is not a part of the number system here, 9 is considered here. Okay, so that is also fine. So you follow the same process. You convert this into a decimal equivalent and then convert that back into the number system with base 6. Okay, so here you are getting 301 as a remainder, and if you consider 16, then again you can consider different combinations, 16 and 8, 10 comma 2. Likewise, you can consider any combination. So as I said here, 10 comma 2, this combination is not possible because you can have values only from 0 to 4. So you have to choose your values accordingly. Okay, let us move on to the what you call as the signed numbers. Okay, I think these are examples that we have seen. Okay, now we are going to look at a most important part, which is called as the signed and unsigned numbers. What is an unsigned number first? Here it is, we are going to let us deal with only the binary numbers and the decimal equivalent here. What do you mean by an unsigned number? Unsigned number is, say, all the positive numbers we are representing, right? So say for example 0 to, in this particular example, if you consider an 8-bit number, then what is the minimum number? So 0000, 8 times 0 here, the decimal equivalent is 0 here. So, and what is the largest possible 8-bit number? Largest possible 8-bit number is 1111. And what is the decimal equivalent? Decimal equivalent is going to be 255. Okay. So, this is as an unsigned binary number, which means we are not putting either it is plus sign or it is minus sign. So, normally all positive numbers are represented as unsigned numbers. Now, say you want to represent a number to say 10. 10 can be represented using 8 bits, right? Similarly, till 255, you can represent using 8 bits. If I want to represent 256, then what you do? Then you will go for additional bit, right? So in that particular case, you can use 16-bit number. So, to put it in a simple terms, if you are representing, say for example 7, what is decimal equivalent of a 7? 111. So you are representing in terms of 3-bit number. If you want to represent 8, then what you do is you have to represent a 4-digit number, 4-bit number, which this will be a 4-bit number, and though you are trying to represent only 8, you can still go ahead with a maximum number of 1111 for a 4-bit number, which means that you have to go, the maximum number now will be 15, right? So that is the same reason here. So if you want to represent 256, then you will have to go for a 9-bit number. Normally, the computers, we used to operate as 2 power 8, 2 power 9, etc. Right? So 2 power 9, you consider, then you have to consider 2 power 9 to represent 256 value. Now, if you look, how do you represent a negative number? Okay. In case of decimal, it is always easy. How do you represent a negative number? If I want to represent plus 25, if I want to represent 25 and I want to represent a positive sign for plus 25, I just put a plus sign. If I want to represent minus 25, it is fairly simple that I put just a minus sign here. These are humans will easily interpret the plus and minus signs here. But the computers, they don't interpret what is a plus sign and a minus sign. So what we should do here? So what computers will understand is they will understand only in terms of binary terms. So in terms of binary terms, in the sense, we are going to represent, we are going to allocate if one particular bit to represent this particular sign. Say I'm representing 8. Okay, let me consider for example an 8-bit representation. Here 8-bit representation, in the sense what will happen? So 4 zeros and then one more 4 zeros, right? This is the minimum 8-bit number that is possible. If I want to represent a decimal equivalent of 10, plus 10. How do I represent plus 10 here? It is 0, 0, 0, 0. 1, 0, 1, 0 is the decimal equivalent of plus 10. Now minus 10, how do I represent? Minus 10 is represented as 1, 0, 1, 0 as usual. So this represents the magnitude part. And in order to represent this sign, one bit is allotted. Mostly, the most significant bit here is allotted for representing the sign, which means minus is represented as 1 here and rest all it is 0. So here, though the capacity of an 8-bit number is 255, that is 2 power 8, 255, here, since you are using 1 bit for a sign, its capacity or its magnitude of representation gets reduced by half. So you can represent only negative minus 128 to 127 to plus 127 using 8-bit numbers. Though the magnitude of representation is larger, so your representation magnitude gets reduced from 255 to 127 here. Okay, so we will see that particular table. Let's go through here. So yeah, so computers, they must represent everything in terms of binary digits. So if you are performing an 8-bit addition, then if there is an overflow, say for example, you are performing 10000000, and you are adding with 1100 and 1100, right? So the sum will be, what will be the sum? This is 100, likewise, and then 1 plus 1 is 0, and then there will be an overflow or a carry. So this but computer is going to recognize, since there is a hardware limitation for your computer, they will look only these 8 bits only. They will not bother what is happening to the carry or something, right? So normally they are programmed in such a way that once there is a carry, there is an alert that is generated using something called as a carry flag in microprocessors. Okay, now most important thing is, how is this signed representation possible? Right, so far we have unsigned means all positive numbers are unsigned representation here. How is the signed integer representation possible? Now, if you want to represent some numbers, something like minus 27 plus 56 or minus 35, how this negative sign and the positive signs are encoded is, as I said before, there are three different solutions here. We will discuss one by one. The first solution is an extra piece of information to be encoded with the magnitude, which means that I have to add whether it is a plus sign or a minus sign. And how can you do that? There are three different ways. First way is a signed magnitude representation, the one that I said you now, right? This way of representing is called as the signed magnitude representation. A signed magnitude representation. Now, next, there are, as I said, there are three different ways. One is called as a signed magnitude representation. Second way of representation is called as a signed ones complement representation. There is a disadvantage with these two things. There is a disadvantage with this, there is a disadvantage with this. In order to avoid these two disadvantages, we are going in for the third one, which is called as a signed twos complement representation. There are other ways of the signed ones complement, which is called as a diminished radix complement representation. What you are doing is, your base, if you represent your base as R, right? In case of signed ones complement represent, you will diminish this particular radix, which means you will reduce this radix by 1. That is the meaning of a diminished radix complement representation. Second is that signed twos complement. The other name of signed twos complement is radix complement representation, a simple radix complement representation, right? So these are the different solutions. First, let us take the first one. What do you mean by a signed magnitude representation? So the signed magnitude representation, normally your most significant bit is used for representing your sign. So always 0 is represented for positive sign and 1 is represented for negative sign. So normally the format here will be looking like this. If it is an 8-bit number, then we will have 8 different bits. right? 1, 2, 3, 4, 5, 6, 7, and 8, right? So always this particular bit here will be representing the signed bit. If this particular bit is 0 here, then it means that the number that this 8 bit is representing is a positive number. If this particular number is a, if the signed bit representation is representing 1 here, then it means that this is representing a negative number. Okay, we will see some examples here. So positive numbers are same as unsigned numbers, obviously, right? Because what is an unsigned number? We don't put any sign here, right? So if it is 0, the positive numbers are represented as an unsigned number here. So as an example, let us see. How do you represent plus just 9? This is an unsigned representation. Why it is an unsigned representation? Because I have not put any sign, and at the same time in my bit representation, I am not allotting any bit for any sign. So this is an unsigned representation. Hence 9 is represented as 1001. Now in case of these two are signed representation. These two are signed representation. And how is 9 represented? 9 is represented as 1001. But since I have to represent a sign that is a plus 9, I am adding one more bit to represent my sign. Similarly, minus 9 is represented as minus 1. And what is this particular technique called? This technique is called as the signed magnitude representation. You are representing the magnitudes with a sign. Okay. Now let us take slightly a larger one, an 8-bit signed representation. So plus 5 is represented as it is plus. Hence your first MSB is 0 here, which is written in black letter here. Rest all it is represented the magnitude of 5. So in terms of the hexadecimal equivalent, it is represented. So how do you do the hexadecimal equivalent? You group into 4, right? So this particular group is 4 and this is a group of 4. So this equivalent is 0 here and this equivalent is 5 here. So 0, 5 to the base 16. Similarly, if it is a 4-bit representation, I'm having 3 bits to represent my magnitude, and the first bit is used to represent my sign. So it will be 0, 5. What about minus 5? If it is minus 5, then my MSB here will represent 1 here. So this represents minus, this represents it is minus, and the magnitude of 5 is minus 5. And again, when you convert to hexadecimal equivalent, so because this is very important so that you visualize it better. So when you group this into 5, so this is a group of 4 and this is a group of 4. So what is 100 in hexadecimal equivalent? It is equivalent to 8 and 0101 is equivalent to 5. Please note plus 5 is represented as 05 and minus 5 is represented as 85 in terms of hexadecimal equivalent. Similarly, an 8-bit plus 127 is represented as it is plus here, hence the first bit is 0 and it is 1111. Minus here, hence the first bit is 1 here, rest all it is 111. What is the hexadecimal equivalent of the 01111111? It is 7F, because this particular group it is 7 and this one it is F. Okay, in terms of hexadecimal equivalent. Similarly, for minus 127, this corresponds to F and this also corresponds to F. So FF in terms of hexadecimal equivalent. If you represent, but there is a problem. What is that particular problem? You can have in magnitude representation, you can have plus 0 and minus 0 also, right? So if you have plus 0, then it means that this bit is going to be 0. If it is minus 0, it is this sign bit is going to be 1. So the hexadecimal equivalent is 00 for plus 0 and 80 for minus 0. Though practically there is nothing like a plus 0 and minus 0, still if you are following the signed magnitude representation, 0 is represented in two ways. One as 00 and other as 80. 0 is a positive 0 and 80 is a negative 0. Okay, so In general, if you want to represent an n bit, it can be represented in terms of signed integers as minus 2 power n minus 1 to 2 power n minus 1 minus 1. How did I do this? Say, as an example, if I consider an 8-bit representation, this is an 8-bit representation, right? So what you are seeing here is an 8-bit representation. So what is the minimum value of 8-bit? It is 0 is the minimum value of 8-bit. And what is the maximum value of 8-bit that is possible? It is 255 is the decimal value which you can represent using 8 bits. But whereas here, because you are taking away 1-bit representation for representing your sign, you are representing only 127 in positive magnitude, and negative magnitude you are representing one more 127. So if you draw a scale like this, if you draw, maybe I'll draw it again. If you are drawing a scale like this, okay, in normally for an 8-bit representation, your minimum value was 0 and your maximum value is 255. In normal unsigned representation, in case of a signed representation now, okay, in case of a signed representation, so this is going to be a signed representation here, you can, a minimum value is minus 127 and maximum value is plus 127. At the same time, I'm having two zeros here, one zero representing minus 0 corresponding to 80 to the base 16 hexadecimal equivalent, and same 0 can be represented as plus 0 corresponding to 00, right? So this is the funniest part here. You are having plus 0 and minus 0. And to look at, so in general, how can you write an n-bit representation is using this representation, which is minus 2 power n minus 1 minus 1 to 2 power n minus 1 to 1. If you don't remember this, just let us apply some value and see. If you consider n equal to 8, then this is going to be 8 minus 1, which is 7. This is going to be n minus 1, which is 7. What is 2 power 7? 2 power 7 is 128. 128 minus 1 is 127. So here also 128 minus 1. So this is equivalent to minus 127 to plus 127. So that is what we have drawn in this particular time scale. Okay, so from minus 127 to plus 127, it is represented. Now, what is the advantage of this? It is simple and easy for your computer to encode. Okay, the negative numbers are identical to your positive numbers. Only difference here is only your sign bit is changing. You see here plus 127 and minus 127, all the bits are same here. All the bits are same maybe. Yeah, you see here that here it is all the bits are same. Magnitude bit is same for positive number and negative number. Only difference here is in the sign bit here. Okay, so this is one advantage. So which means if any number I give, say for example, I ask you to find out what is the signed representation of 1 0 1 0. What is this signed representation of this particular number? This is equal to what? Anybody can you say? This is a signed representation. This is a signed representation of magnitude. This is equivalent to minus 2. So which is, so what is plus 2? Plus 2 is just 0 0 1 0. So this is going to be plus 2. So easily I can interpret what is this particular binary value. So these are some of the advantages of this system, but there are more disadvantages. What is the disadvantage is you are representing zeros in two different ways, plus 0 and minus 0. And at the same time, let us take one example. If you add plus 10 and minus 10, what must be your answer? It must be 0, right? But you will not get 0. Let us see how. Let us see how is. I'm taking an example here. If you take plus a and minus 8 should be 0, but it will not be 0. Let us take an example. You know that plus 5 is represented as 0.5 in terms of hexadecimal value, or let me do it here. How is plus 5 represented as plus 5 in terms of represented as 0, 1, 0, 1. Okay, so its hexadecimal equivalent is 0.5 to the base 16. Now minus 5 is represented as 1101. What is 1101? 1101 equivalent is, okay, let us take an 8-bit representation. So that would be easier. Yeah, let us take an 8-bit representation. So if it is an 8-bit representation, so zeros represented as 4 zeros and then 0, 1, 0, 1. Okay, in terms of binary. So hexadecimal equivalent is 0, 5 to the base 16. Now minus 5 is represented as, your sign bit will be 1 here, 0, 0, 0, and then the magnitude part 0, 1, 0, 1 to the base 2. This is equivalent to 8, 5 to the base 16. When you add this, it must be 0, right? So here, when you add this will not be 0. When you add this, 5 plus 5 is going to be 10. You have to convert to decimal and then you have to add, right? So when you add, it is 85 plus 0.5, right? 85 plus 0.5. What is 5 plus 5? It is 10. 10 is represented as A in hexadecimal, and then 8 plus 0 is 8. So 8A to the base 16 is what is the answer when you add two complement numbers, which is not, this is not equal to 0. This is not equal to 0, right? So hence this is a serious disadvantage with this signed complement number, signed magnitude representation. And also you have to, when you are doing arithmetic calculations, you have to create a complement circuits. It will require complicated arithmetic circuits, right? If you are creating if you are performing this addition subtraction, you have to create arithmetic circuits for that. So that is slightly very difficult here. So in order to avoid this particular problem, what people thought is you have to have a complement way of representation. So complement way of representation in the sense, say if I am representing 5, okay, so it is 0, 1, 0, 1 as a normal representation. So let us represent minus 5 as 1, 0, 1, 0, which means a complement of this. 1 is changed to 0, 0 is changed to 1 here. And when you add this must be equal to 0. So that is what people thought, and that also had certain disadvantages. Let us see what are those particular disadvantages. So positive numbers is similar to the unsigned numbers only. Okay, so in case of ones complement number, the positive numbers ones complement representation is same as that of your unsigned number. Meaning, if it is plus 5, it is similar to the signed representation. Plus 5 here is represented as 0, 1, 0, 1. And normal 5 without unsigned 5 is also represented as 0, 1, 0, 1. So both representations are same. But the negative number is represented as minus 5 is represented as complement bits. So 0 here is represented as 1, 5 is represented as 0, 1 and 0. So this corresponds to minus 5. So yeah, the same example that I have taken. So minus 5 in ones complement representation we are going to look. In case of 8-bit representation, I just showed you a 4-bit representation. Now let us look at an 8-bit representation. So plus 5 here in terms, it is 0, 0, 0, 0, 1, 0, 1. So its hexadecimal equivalent is 0.5 to the base 16. Its ones complement is complement everything. So this becomes 1, 1, 1, 1, 1, 0, 1, 0, right? So which is the same as this particular number. And what is the hexadecimal equivalent? Hexadecimal equivalent is FA to the base 16. Now you can always see that FA is a complement of minus 5. Okay, so that is what we have done here. Similarly, let us take more example here. Plus 127 can be represented as 01111, which is equivalent to 7f. Why 7f? This corresponds to 7 and this corresponds to f. Minus 127 corresponds to, this corresponds to 8, this corresponds to 0. So when you add, what you will get is, you will get ff. Okay, so you add these two things. What is plus 127 and minus 127 equal to? It should be equal to 0. Here, if you add these two in hexadecimal equivalent, what is f plus 0? F plus 0 is f. 7 plus 8 is 15. 15 equivalent in hexadecimal is f. So what is ff equivalent in this number system? Let us see. It is also equivalent to 0. So plus 0 is represented as 0000 and minus 0 is represented as 1111, which is equivalent to f. So here, if you add, you are getting ff, which is equivalent to 0. So that is fine. So the previous disadvantage which we had, when we add, it was not getting 0 right here. If we add, this was not equivalent to 0. But here we are getting an equivalent to 0. But the disadvantage here is still we are having the same problem of representing the plus 0 and minus 0 here. Okay, in general, they can be represented in the same way from minus 2 power n minus 1 to minus 1 to 2 power n minus 1 minus 1. So in case of 8 bits, it is from minus 127 to plus 127. So the problem of still 0 still persists here, right? So there are two zeros here representing plus 0 and minus 0. Mathematically, nothing of that particular sort exists. But if you add, you are getting 0. You add plus a and minus a, you will get 0. You add minus 5 and plus 5. Minus 5, we have already just saw that it is equivalent to how much? fa. So let us add here. Minus 5 is equivalent to fa and plus 5 is equivalent to 0.5. Right? So what is a plus 5? 10 plus 5 is 15. 15 is represented as f in hexadecimal and f plus 0 is f. And what is this equivalent to in this number system? ff is equivalent to minus 0. So still you are getting a value equivalent to 0 here. So if you add, you are able to get the exact result, but there are two zeros here, plus 0 and minus 0. And at the same time, if and another limitation here is, if you add a plus 0, it is 0, it works fine, you get plus 0, right? You can also, instead of this 0, since you have two zeros here, plus 0 and minus 0 here, you must also get a here, right? So you must also get a here. What is a plus 0? It is a. Here you have got two zeros. So a minus 0 must also be a, right? But here it doesn't happen. So what happens here is, say 5 plus 0, 5 plus in terms of hexadecimals, 5 plus 0 is 5. This is absolutely fine. Now 5 plus minus 0, if you took, you must get 5, but minus 0 can be represented as ff. So if you add ff plus 0.5, when I am adding ff plus 0.5, please note it is 15. 15 plus 5 is 20, which is represented as 4. 16 plus 4. Okay, so 20 minus 16 is 4. So 4, and then there is a remainder 1 carry here. So it will be 0 here, and then there is a remainder 1 carry. So let us discard this carry. So its resultant is equivalent to 0.4 to the base hexadecimal, but so the answer is wrong here. So if you are adding any number with a negative 0 here, you are not getting the desired result. So we have to avoid this representation also. So how do you manage this is, we go in for a signed 2's complement representation. What is a signed 2's complement representation? A signed 2's complement representation is, we have already seen this, it is 1's complement plus 1. Meaning you take 1's complement as before in the previous case, add 1 to it. Okay, so if how is minus 5 represented in 2's complement here is, in case of any 8 bit, we are operating on 8 bits here. Plus 5 is represented as 0, 0, 0, 0, 0, 1, 0, 1. Minus 5 in terms of 1's complement is you complement everything. 1, 1, 1, 1, and then 1, 0, 1, 0. You add 1 to it. If you add 1 to it, then what will happen? 1, 0, 1, 0 plus 1 is 1, 0, 1, 1. And then 1, 1, 1, 1. And its hexadecimal equivalent is FB. So this is the FB is the 2's complement representation of minus 5. We have to check now. If you add plus 5 with this, you must get 0, right? So we have to check that. Let us see. More examples. 127 is represented as 7F. 0, 1, 1, 1, 1, 1, 1, 1 is represented as 7F. And 2's complement. Please note it is 127. First you have to take complement. Let me do here. 1, 0, 0, 0, 0, 0, 0, 0. This is the 1's complement. This is the 1's complement of this number. But we need 2's complement, so you have to add 1 to it. So what you will have? You will have 1, 0, 0, 0, 0, 0, 0, 1. So which is the 2's complement form. So the 2's complement equivalent in hexadecimal is, in the previous case you got 80 as a 2's complement value. Sorry, 1's complement value. Since you are adding 1 here, it is 81. So you add these two things. So what is plus 127 and minus 127? You must get 0, right? If you add, you will get 0. What is f plus 1? F is 15. 15 plus 1, you go to the next bit, right? So it is 0. What is 7 plus 8? 15, and there is one more remainder carry from here. One more remainder. So it will be 16. So it will be 0 and 1. So if you look only these two bits, they are equivalent to 0. Okay. Similarly, let us take the plus zeros and minus zeros. Plus 0 is represented as 1, 1, 1, 1. Sorry, 0, 0, 0, 0. And the 1's complement of this will become 1, 1, 1, 1, 1, 1, 1, 1. And I have to add 1 to it. If I add 1 to it, then it will be 0, 0, 0, 0, 0, 0, 0, 0, and 1 carry. We ignore this carry. So still you get the 2's complement of minus 0 is also 0. So you are having only 1 0 equivalent here. So hence, yeah. Now in the previous case, we had 80 getting represented as minus 127, right? So now what is the equivalent of 80? In the previous case, if you look in this 1's complement form, please see here that 127 is represented as minus 127 here is represented as 80H. So here let us see in 2's complement form what is 80H equivalent to. 80H is equivalent to minus 128. So minus 128 will go beyond the limits of this 8-bit representation. Okay, it will not go beyond the 8-bit representation. Instead, in 7-bit in 8-bit representation, you are trying to represent one additional negative number in case of a 2's complement form. Or if you ask me to draw the graph here. Okay, I think it is, I already have somewhere. Yes. In case of a signed magnitude representation, you see here, we had minus 0 and plus 0. What is the limit? FF was represented as 127 here, and 7F was represented as minus 127. In case of 1's complement, you still had minus 0 and plus 0. 80H was represented as minus 127. 7F was represented as plus 127. But in 2's complement form, that is the advantage. 0, you have only 1 0. In positive side, there is no change, plus 127. Whereas in the negative side, you had 81 getting represented as minus 127. In addition to that, 80H is represented as minus 128. So you are trying to add one more negative range along with 80H. Right? So these are some of the advantages here. Whereas the signed magnitude representation and unsigned magnitude representation, unsigned magnitude representation is absolutely similar to what you have it in the positive side of your signed representation. Okay, and what is the range here? Your negative range, as I said here, since you are representing from minus 127 to minus 128 to plus 127, for an 8-bit, you are representing from minus 128 to plus 127. In case of ones complement, you are representing from minus 127 to plus 127, plus 127 to. In case of a signed magnitude representation also, it is minus 127 to plus 127. In these two cases, you had plus 0 and minus 0, right? This minus 0, this extra bit representation, now it is taken care by an additional negative value range of minus 128. Any doubt here? Any doubt?
Excuse me, sir.
Yes.
Sir, by 80H you mean 80 in hexadecimal digits, right?
Yes, 80 in hexadecimal digits. So,
Okay.
yeah, if you want, like, we can convert. What is this 80H corresponding to? It is 1000000H, right? So this is in terms of um, binary digits. You convert this into decimal equivalent. The decimal equivalent will be equal to 128. Will be the decimal equivalent of this. Okay, sorry, not 128. It's actually minus 128. Why minus 128 is because this one is a sign bit which is taken by the minus. That is the reason.
Okay. And
Okay.
sir, can we represent minus 5 in 6 hexadecimal but 4 digit? 4 bits, sorry. 4
In
bit
4
number.
bits, yes, you can definitely represent. In that particular case, it will be 1 for a signed representation. So there are three ways. Good. Thanks for asking. So there are three different representation, right? Minus 5 can be represented as 1, 1, 0, 1 in terms of signed magnitude representation. In terms of signed magnitude representation. This minus 5 can be represented as, so 0101 is a plus 5 representation. So in terms of ones complement representation, they can be represented as 1010 in terms of ones complement representation. In terms of twos complement representation, minus 5 can be represented as 1011. Why? Because I am adding 1 to it. Right? So these are three different ways of representing minus 5. Okay, whereas plus 5, it has got only one representation similar to the unsigned representation. So minus 5 in terms of signed magnitude representation can be represented as 101. In terms of ones complement, it is 1010. In case of twos complement, it is represented as 1011. But computers, we prefer only twos complement representation. Why twos complement representation? Because we have already seen the multiple advantages. We have only 10 here. We are getting an extended range of uh, the values from minus 128 to plus 127, which is not available in the other two signed representations. Okay. Any doubts so far?
So by that I meant that we write minus 5 as 85 to the base 16
Yes,
in
correct.
8, but we consider that as 8-bit representation. So
Yes,
in
it.
that, if we take 4-bit, how will we represent it in hexadecimal?
Okay, that's what I did. In case of a 4-bit representation, so in terms of hexa, this is going to be how much? What is the in signed magnitude representation? What is 1101 in hexadecimal? I think 1010 is A, 1011 is B, 1100 is C, 1101 is D. Okay. So in signed magnitude representation, minus 5 is represented as D to the base 16. In ones complement representation, it is represented as A to the base 16. In twos complement representation, it is represented as B to the base 16. If you want, You can add and see also. Plus 5 and minus 5, right? So what is plus 5 and minus 5 correspond to, sorry, this is minus 5 and this is plus 5. What is B is equivalent to what? B is equivalent to 11, right? B is equivalent to 11. So 11 plus 5 is 16. 16 will be equal to, can be represented as F plus 1. So which means it is 0, 0 with a carry of 1. So you are getting still a 0 value.
Okay, sir. Thank you.
Thank you. So, all right. So we will continue this particular thing in the next class. Next, we have the complement representation, which we have already seen. That is 9's complement, 10's complement, 1's complement, and 2's complement. Okay. So if there are no doubts, you may leave the class.